So coming towards the lecture now. So lecture number 28 today's related to thermodynamics 2, and again it is from rotordynamic machinery. So can anyone confirm my voice is audible, or is there any
Yeah,
noise from my side?
sir,
Yes, sir,
audible.
you are audible and the slides visible.
Okay, so we will discuss just the last topic. Okay, so in the previous class we already talked about the velocity diagram that is for the impulse turbine, that is at inlet and outlet. I hope you already practiced that, and because I will suggest you have to draw it by yourself, because it may be possible that I will give that type of question that you have to draw the velocity diagram of blade inlet and outlet. Okay, so you have to be practice it, otherwise it will be very difficult for you to draw the paper. Okay, so this is the velocity diagram for the inlet and outlet and all the parameters. So today in the today's lecture we will discuss something about problems that's related to the impulse turbine, and more specifically related to the velocity diagrams. So this is the combined velocity diagram. I hope you already know that how you have to develop the combined velocity diagram. Plus, you just have to join inlet and outlet velocity together, and the vector diagram will be there. Okay, so now coming towards the question, and all these formula I already discussed in the last lecture, because these formula we have to directly use. Okay, another important thing is that usually this type of combined velocity diagram problems are not very easy. The reason is that whenever we are teaching these type of courses, that is the thermodynamics, we do not focus at how to draw these type of diagrams accurately by using the scales. Because for example, if you are study the main course related to the rotordynamic machines, okay, so it will be not like this that these diagrams are given to you. Okay, so you have to draw these diagrams by using the scales. Okay, and then by measuring the length you can get the v1, by measuring the length of each vector you get the velocity, by measuring the angles you get the beta or alpha, whatever the angle is. But in this course I will try to provide all the data with this diagram, so you just have to use the specific formula to find out some specific parameter. Okay, so I will just make the things easy for you rather than making them more complex. Okay, so coming towards the first question, that is related to the combined velocity diagram. The steam with absolute velocity 360 meter per second enters the stage of an impulse turbine. The nozzle are inclined at 20 degree to the plane of the wheel. So from this data you can easily find out that this is basically absolute velocity. Okay, absolute velocity you can say at the outlet of the nozzle is given, or v1 is given in the question. The nozzle are inclined at 20 degree, so alpha 1 is given because the nozzle inlet angle is alpha 1. The blade rotor with the diameter 95.5 centimeter. This I will tell you that how to use this type of data. The speed of 3000 rpm. Find mean blade speed, power dweller, kinetic energy of steam leaving the stage. Okay, the three parameters you have to find out by using this combined velocity diagram. So every time whenever you see this type of problem, the velocity diagram is mentioned and all these parameters are also mentioned. Okay, so do not worry that how you have to find out these parameters. Okay, so if you can look into the diagram, we have V1 with us, blade inlet angle is given, blade outlet angle is given, combination of whirl velocity at inlet and outlet is equal to 348 meter per second, absolute velocity at steam of steam at exit V2 is given. Another thing is that in the part A we have to find mean blade speed, and mean blade speed is already mentioned in the question. So for example, if this mean blade speed is not mentioned over there, okay, so then how you can figure it out, what is the mean blade speed? So power dweller we can easily find kinetic energy of steam leaving the stage. We can also find by using, because if you can notice that kinetic energy leaving steam leaving the stage, so leaving the stage mean we are interested in absolute velocity at outlet. Okay, so absolute velocity at outlet is also given, so we can easily find. So first you have to note down the data and make the figure, and then we will see how to solve it. Okay, so coming towards part A. So part A is very simple. So if the blade velocity is not given, so you can easily find mean blade speed, that is equal to u, and the formula is pi, diameter of the blade, number of rpm divided by 60. Okay, so simple, you have to use this formula because diameter of blade is mentioned. So 3.14 value, diameter of blade is 0.955. It's come from the problem statement. Number of rpm is also mentioned in the problem statement, 3000 rpm divided by 60. So if you can solve it, you will get the part A answer, which is 150 meter per second. Okay, so in case the mean velocity, mean blade speed is not given, so you can easily find out by using this simple relation. So part A solution is complete. Now coming towards part B. So in part B, we have to find power value. So power value formula we already know: mass flow rate, VW1, VW2. Okay, so this formula we already discussed in the last class as well. Divided by 1000. Okay, so that you will get the units in kilowatt. So in this case, okay, another important thing is not mentioned in the problem statement that mass flow rate you have to use 1 kg per second. So in case if there is any other value that is given in the question, so you have to put it. So here you can just assume that it is 1 kg per second and you can put the value of 1. The value of VW1 plus VW2 is mentioned in the question, which is 348. Blade velocity U we have just find in the previous step, 150, and this is just a conversion for your watt to kilowatt. So here if we get the answer, it is 52.2 kilowatt for the power level. It's a very simple question. So now coming towards the kinetic energy, that is C part. So where we have to find kinetic energy of steam leaving the state. So steam leaving the state, it's mean we are interested in absolute velocity at the outlet. For example, in the same case here it is mentioned that you have to find kinetic energy at steam entering the stage. Okay, so then you are interested in V1, which is the absolute velocity V1. Okay, so in this case simply we use half m V2 scale. M is basically 1. Okay, so 1 by 2, 1, and V2 value is mentioned in the question. So this you can find out that this is 79.38 Newton meter. Okay, so this is the kinetic energy for parts. So solution is complete. So very easy solution. So you have to note it down. Then we will discuss the next problems. Okay, so coming towards the next question. So it is also very simple. So here it is mentioned that the blade speed in the impulse turbine is 300 meter per second. So U is given in the question. Nozzle angle is 20 degree. Alpha is given. Total energy supplied to the blade is 473 kilowatt. So this I will tell you how to use this data. when we are going to solve the problem. So calculate for mass flow 1 kg per second. Fourth thing which is required, A is the axial thrust per kg, brake power, mechanical efficiency is 90, blade efficiency, and stage efficiency. Okay, so these all things you have to find out. So beta 1 is equal to beta 2, the angle is given, the bulk velocity at inlet and outlet addition is given, axial velocity minus axial velocity at outlet is given, relative velocity at 1 is given, relative velocity at 2 is known. Okay, so you have to draw this figure and also note down the data and then see how to solve it. Okay, so part. So in the part A, we have to find axial thrust. Okay, so I already told you whenever we have to find axial thrust or axial force, you have to consider for the velocity components that are axial. If we want to find the tangential force, we have to consider for the tangential component, that is the VW1 and VW2. So here the formula is M VA1 minus VA2. Okay, so this is one, and the value of VA1 minus VA2 is mentioned in the question, which is 92.5. So by using this relation, you can easily find that this is 92.5 Newton. So this is the answer for part A. Very simple one. Coming towards part B. So in part B, we have to find the brake power. Okay, so I hope you already know what is the meaning of brake power. So basically, brake power, uh, if we are considering any friction force, okay, for example, if the blade is steam is hitting with the turbine blade and there is some friction, and due to that friction, there is some losses, and in order to cater these losses, we have to find the mechanical efficiency. So simply you have to find the brake power by multiplication of power dweller multiplied by mechanical efficiency. So in case mechanical efficiency is given in the question, you can easily put, or otherwise you can find out also. Okay, but in this case, the mechanical efficiency is mentioned in part B, which is 90%. So power dweller formula we already seen in the last class, which is M VW1 plus VW2 into blade velocity divided by 1000. Okay, so this is one VW1 plus VW2 mentioned in the problem statement 927. Blade velocity 300 is also mentioned in the question, and divided by 1000, so it is equal to 278.25 kilowatt. The power developed we are fine. Now we can easily find the brake power, which is equal to 278.25 multiplied by 0.5. 9. So this is equal to 250.425 kilo. So this is the answer of part B. So you have to note it down, then move to part C also. So moving towards part C. So part C is to find the blade efficiency. So blade efficiency formula we already discussed in the last class. The simplified version, that is 2U VW1 plus VW2 divided by V1. So U is basically blade cost. So here we have all the parameters with us. U is 300 meter per second. VW1 plus VW2 is 927.5. V1 square is 900 square. So here we get the blade efficiency, which is 0.688, and it is equal to 68.8% of your blade efficiency. So this is part C solution. And now moving towards part D, where we have to find the stage efficiency. So I can write that theta stage. Theta stage we have already seen the last lecture, the formula, which is work done on blade per second. So basically this is power, okay, in kilowatt, and energy supplied to the blade. So if you can notice from the problem statement, we have the parameters, that is the value of energy supplied to the blade is given to us. Okay, so simply you have to put the value, because this parameter we have already defined in the part B, which is the power. Okay, so its value is 278.25 divided by energy supplied to the blade is in 470. Okay, so here important thing is that this is in kilowatt, so that's why I have put the kilowatt over there. So either you can convert this into watt, and then you can use this value also in watt, by conversion of 278.25 into watt. So the thing is that you have to make the unit consistent. Okay, otherwise it will be not a correct answer. So here we have 0.5 AA, and the stage efficiency is 58.8%. Okay, so I hope you know that what is the meaning of stage. The stage means a combination of your fixed blade and moving blade. So collectively, the stage efficiency means the efficiency related to the first set of blades which contain moving and stationary. So this is the solution of your uh, second question. So you have to note it down. If you have any question, you can ask me. Then we'll go to the next. So coming towards the next topic, which is also one of the important topic, but we are not going into much detail. We just look into briefly at what is the meaning of compounding in steam turbine. Basically, whenever we are going to design the steam turbines, our main purpose is to design a turbine in such a way that we get some optimal value of the rotation in the turbine. Okay, for example, if we are getting more speed and we are not, and it is not required for us to obtain that such speed, so it is not useful for us to develop such a turbine where we are getting more speed as per our requirement. Okay, so in order to do that, to control the speed, we use a term that is compounding. Okay, so if we can just take a look for the specific definition of compounding. So compounding is the way of reducing the wheel or rotor speed of the turbine to optimum value. And sometimes this term is also called staging. Okay, staging or compounding. So the term is meaning is same. So it may be defined as a process of arranging the expansion of steam or the utilization of kinetic energy or both in several. Okay, so basically, if I just want to look into the meaning of this statement, so compounding is just an arrangement of different parts. Okay, for example, if you want to arrange some specific blade location, that is a stationary and moving blade, to some other location, or you can say in specific arrangement, that is nozzle is at the start of the moving blade or nozzle is at the start of the fixed blade. Okay, so these all type of arrangement is called basically compounding, by which we can reduce the wheel or rotor speed. So there are several methods of reducing the speed of rotor to lower value. And all these methods utilize a multiple system of rotor in series keyed on a common shaft, and the steam pressure or jet velocity is absorbed in stages as the steam flow over the blades. So usually we have two methods, okay, velocity compounding and pressure compounding, or you can say velocity staging and pressure staging. And there is also third way, that is or method, that is the combination of pressure and velocity, or we can call as a pressure velocity compounding. So here we can only discuss velocity and pressure compounding so that we will just get the overview of this term. So coming towards the first method of reducing the rotor speed, that is the velocity compounding. So if we can just look for the theory first. So there are a number of moving blades separated by ring of fixed blades. All the moving blades are keyed on a common shaft. When the steam passes through the nozzle where it is expanded to condenser pressure, its velocity becomes very high. This high velocity steam then passes through a series of moving and fixed blades, and when the steam passes over the moving blade, its velocity decreases. The function of the fixed blade is to redirect the steam flow without altering its velocity to the following next row moving blade, where a work done on them and steam leaves the turbine with allow velocity as shown in diagram. So if we can just take a look at the meaning of this whole paragraph, you can say. So meaning is that we have to arrange in a velocity compounding the moving blades, then there is a fixed blade, okay, and all these blades are of same shape. Okay, so we will see with the help of diagram also. Okay, and main purpose of the fixed blade in the velocity compounding is just to redirect the flow. Okay, so it has not any other purpose. So the arrangement in which there is a moving blade and there is a fixed blade, and by which we can reduce the velocity of the rotor, so it is called velocity compounding. And from the pressure velocity diagram, from here we can easily see that in the velocity compounding we have nozzle, that is the fixed nozzle. We have the moving blade, this is the fixed blade, again moving blade, fixed blade, and moving blade. So the purpose of the fixed blade, for example, if there is a flow is coming from the nozzle and it hits your moving blade, so in order to redirect the flow again to the moving blade, the fixed blade is used. So fixed blade just reorientate the flow towards the moving blade, and in the same pattern, it will just try to redirect the flow. So this is just a basic purpose of the fixed blade in the velocity compounding. So if we can look into the pressure velocity diagram, so the pressure decrease at the end of the nozzle, then as the steam passes through the moving blade, so it's remain constant, and then there is stationary blade, so it's remain constant in all the stages. So at the end of the stages, so collectively we call this one as a one stage. Okay, moving blade plus fixed blade. So this is another stage, and then there is another stage. So the pressure remain constant in the velocity compounding method. Now coming towards the velocity diagram. So velocity is increased at the end of the nozzle. Then as it passes through the moving blade, because there is the absorption of kinetic energy, so definitely velocity decrease. Then in the fixed blade, because the fixed blade purpose is just to reorientate the flow, it has no other purpose, so velocity remain constant in the fixed blade. Then again the moving blade, the velocity further decrease, then it's remain constant for the fixed blade section, and then it further decrease. So basically the purpose of this whole arrangement is to just, for example, if I want to get the rotor velocity of 300, you can say just for example meter per second. So I want to make the configuration or number of stages like this, so that I will get this value, and this value is decided by the design engineer or either the requirement that is given to you as a design engineer. So you can design the configuration specific so that you can get the 300 meter per second magnitude at the end of the stage. So this is the velocity compounding method to reduce the rotor speed. So this is just a whole theory. I have already explained to you all the things. So you have to go through it by yourself. Okay, so I think there is nothing difficult inside it. So you can easily understand. So now coming towards the next term, which is the pressure compounding. So basically, this is also another set of arrangement. You can say in the previous case, velocity compounding, we have arranged the fixed and moving blade. So now here we can see what type of arrangement we have to do so that we get the pressure compounding. So there are ring of moving blades which are keyed on a same shaft in series, are separated by the ring of fixed nozzle. Steam at boiler pressure enter the first set of nozzles and expand partially. The kinetic energy of steam thus obtained is absorbed by moving blades. The steam is then expanded partially in the second set of nozzle, where its pressure again falls and the velocity increase the kinetic energy so obtained is absorbed by second ring of moving blade. This process repeats again and again, and at last steam leaves the turbine at low velocity and pressure, and during the entire process of the pressure compounding, the pressure decreases continuously, but the velocity fluctuates as shown in diagram. So this is just a theory, and we will see with the help of figure what is the meaning of this whole. Okay, so in the case of pressure compounding, the arrangement is shown over there. We have the fixed nozzle, there is a moving blade, fixed nozzle, moving blade, fixed nozzle, moving blade, fixed nozzle, and moving blade. Okay, so if this type of arrangement is shown over there, so it is called pressure compounding. And in order to understand the pressure compounding, we just take the pressure and velocity graph. So at the end of nozzle, pressure decreases because there is expansion take place. Then in the moving blade section, the pressure remains constant. Again there is a nozzle, so pressure decreases. Then moving blade, pressure constant, and until it reaches towards the end stage, the pressure decrease. So in case of velocity compounding, pressure remain constant, and in case of pressure compounding, we have reduction in pressure at every stage. Now here, if we can look for the velocity diagram, so at the end of your nozzle, the velocity increases. Then at the end of the moving blade section, due to the absorption of kinetic energy, velocity again decreases. Then there is a nozzle, it again increases, again decreases in the moving blade section, so decrease, increase, so on until we get some reduction in velocity, that is our required value, and to get some optimum speed. Okay, so this type of arrangement is called pressure compound. Okay, so this is again whole theory. Okay, so just for your understanding purpose, so you have to read this whole theory, and you can easily uh, get some information out of it. Okay, so now coming towards just a last slide for this course, or you can say this lecture also. So in case of steam turbine, such as used in electric generation, a reaction turbine would require approximately double the number of blade rows as an impulse turbine for the same degree of thermal energy conversion, while this makes the reaction turbine much longer and heavier, and the overall efficiency of reaction turbine is slightly higher than the equivalent impulse turbine. So here you can easily find out that the overall efficiency of reaction turbine is slightly higher than equivalent impulse turbine for the same thermal energy conversion. Another important information that most of the modern steam turbine use both reaction and impulse in the same unit, typically varying the degree of reaction and impulse from the blade root to its periphery. And the rotor blades are usually designed like an impulse blade at the root and like a reaction blade at the tip. So if you can look the blade configuration, we can easily figure it out that at the root it is more impulse type of blade, and at the tip it is more reaction type of blade. Okay, so why we have to use this type of arrangement in the turbine? So usually our main target is to develop such type of arrangement where we get the maximum efficiency, or you can say maximum with the, if you can give the minimum steam, you are giving you are getting more rotation. Okay, so that in order to get this type of efficiency, or you can higher efficiency, we have to use this arrangement. So there is no hard and fast that you can use impulse at the root, or at the tip you can use the reaction. However, for example, if I am doing research and I can figure it out that this time of arrangement is not giving the maximum efficiency, rather than if I can replace this middle section with a V type of blade, so I will get more efficient blade configuration. So I can easily do it. Okay, so this is just for your information that if you are going in any project or like this, so you can easily alter the design of this blades section, and you can figure it out that what type of efficiency you are getting. Okay, so this is the end of your course, and if you have any question, you can ask me till now, and then we will discuss your paper pattern. Okay, so I hope there is no question. Okay, so you have to go through it all these things by yourself. Okay, so now coming towards paper pattern. So paper is basically very simple. So you have total 5 questions in the paper. Each carries 20 marks. So first question, because usually we there are all questions which we already discussed in the lecture. So that is coming from steam turbine. There is one question. There is one question from gas power cycle. There is one question from chemical reaction. One question from compressible flow, and one question from rotodynamic machines. So if you can notice that we have covered all the course which we already see and we already discussed in these lectures. Okay, so all question, this is 20, 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 and total it is 100. Okay, now coming towards the main thing, that is the formula sheet. So formula sheet I will upload in the team section of MS Team section, in the file section of your channel. Okay, before the paper, or you can say in the next week. Okay, and the formula sheet is uh, you can easily find out that what type of formula you have to just remember it, and what formulas are given in the paper. Okay, and you have to print that sheet with you. Okay, because I'm not giving any formula sheet with the paper. Okay, so you have to take the printout and bring it on the paper. Okay, now second thing is thermodynamic table. So thermodynamic table, you just have to take a print of all the thermodynamics table and bring it with you on the paper day. Also, uh, or also I will upload it in the MS Team section, so you can easily find out the thermodynamic table from here. Okay, so this is just your paper pattern. If you have any question, you can ask me. And paper is most likely the same problems that we already discussed in the class, or either it will be the assigned problems or your assignments. Okay, so there is nothing that is unseen in the paper, or you can say out of course. Okay, and very simple. If you practice all the assigned question, I think you can easily score 100 marks in my paper. So now if you have any question, you can ask, then we'll just start.
Okay.
सही सर theory के part से हो गया theory part भी होगा
जी प्रॉबली थ्योरी पार्ट अभी मैंने पेपर बनाया नहीं है, लेकिन मोस्ट कॉमनली, और यू कैन से yes, I will add one theory question as well. It is not a theory question because it is just like you can say a descriptive question that if I can say what is the meaning of compounding or uh, pressure compounding and velocity compounding, so then you have to just write. So just I'm giving the example, so it is not a part of the paper. So one question you can expect that the theory question as well. So any other question? So I hope there is no question, and we will stop at this point. Just